Welcome. The topic of today's lecture is magnetic ceramics. Although our focus is on ceramic materials, but to understand the properties of this group of ceramics, we need to understand the basics, some of the basic concepts of magnetism, and compare the properties of the ceramics with the other group of materials like metals and alloys. So, to start with, as I mentioned, our topic is magnetic ceramics, and we will first consider a few general concepts in magnetism. These are basic physics. From the undergraduate physics, one can go through this, and some of the relationships. There is a strong correlation between magnetism and dielectric properties, which we will take it up in a minute. So, magnetic induction is basically dependent on the magnetic field we apply, particularly when the environment is vacuum. We can write an equation B0 equal to mu 0 multiplied by H is the magnetic field and B0 is the result of that. So, it is magnetic flux density, or sometimes it is also called magnetic induction. So, B0 is mu 0 H, where H is the magnetic field and mu 0 is the magnetic permeability. We have seen earlier a similar term epsilon 0 in case of dielectric properties or dielectric behavior or dielectric polarization. Here very similar term is there, mu 0 is the magnetic permeability in vacuum. The subscript 0 denotes vacuum here again, and it is a constant with a value of 4 pi into 10 to the power 27 10 to the power 7 Webb per ampere meter. Now, there are various different units used not only for this particular parameter, but in the context of the magnetic behavior or magnetic other parameters in magnetism. The units are volt second per meter, that is the same permeability. It is also written as Webb per meter square, and which is also Tesla, which is nothing but 10 to the power 4 Gauss. So, the measure of magnetic field, in fact magnetic field is there are various different units used in the literature. Instead of vacuum, if we have a material, magnetic material which responds to the magnetic field in some form or the other, then we can write the magnetic induction B mu 0 H plus J, which is J is the magnetic polarization, and J also has a relationship with M is a magnetization, and by that one can write mu 0 H plus M, and from this relationship one can get J, the magnetic polarization, equal to mu 0 chi M. We introduce another parameter which is very similar to the dielectric behavior. Chi M is the susceptibility, magnetic susceptibility, and it is written as chi M equal to M by H. Okay. So, the magnetic polarization here also we are bringing in a term which is called magnetic polarization. J is mu 0 multiplied by chi M multiplied by H. M, as I mentioned just now, is magnetization, and in other words magnetic moment per unit volume. So, this is also a kind of relationship between magnetic moment and the magnetization. as you have told you that the flux density B with a material equal to B equal to mu 0 1 plus chi m h, that is an important relationship, and from which we derive another permeability term, that is the relative permeability mu r into 1 plus chi m. This 1 plus chi m is the mu r. So, this is also magnetic susceptibility as mentioned, and finally, the magnetic induction is mu 0 mu r h. So, it is a proportional, the magnetic induction is proportional to the magnetic field we apply. Okay. Here of course, one should also notice that it is a very closely related to the dielectric phenomena we have studied earlier. So, that gives us a comparison analogy between magnetic and dielectric properties or dielectric parameters. This is magnetic field strength H, okay, and that is ampere per meter, whereas this is electric field strength. So, that is the external field, magnetic field we apply. Of course, there is a correlationship between the magnetic field and the electrical current. Normally, the magnetic field is generated by a solenoid or by a permanent magnet from outside. So, magnetic flux density, the induction, we are basically talking about how this material responds to the external field H. Okay. Here also the dielectric displacement is D. They have a analogy between each other. Magnetic polarization J, and here is the dielectric polarization P, and the units are ampere second per meter square, where is volt seconds per meter square. So, magnetization M, this particular term does not have a real analogy with the dielectric phenomena, otherwise all the terms have some parallel phenomena in both the types of interactions. B equal to mu 0 H plus J, that is mu 0 H plus M, that I have written earlier, and here also the similar expression is dielectric displacement is equal to epsilon naught E plus P, polarization. Here J is the polarization, here P is the polarization, and then once again one can write this expression we have also seen, mu 0 mu r H, here also dielectric displacement equal to epsilon 0 epsilon r E. The polarization can be also expressed in the form of susceptibility, that is mu 0 chi m H here, and here is dielectric susceptibility, this is magnetic susceptibility and that is dielectric susceptibility, and the relationships are very similar. Magnetization again does not have a particular analogy with in the dielectric phenomena. Chi m H, this is not there so far as the dielectric phenomena is concerned. This is mu r equal to 1 plus chi m and epsilon r is 1 plus chi e. So, the two phenomena, magnetic phenomena and dielectric phenomena, are very similar in nature, although there are certain differences, and it will be clear when you discuss further. So, those are some of the phenomenological description of the magnetic behavior of material, and here is we like to understand where from this magnetic behavior comes from. And as we have seen, there are different mechanisms of polarization in dielectric material. Here also there is origin of magnetism in any material. Okay. Of course, dielectric phenomena comes only when we apply an electric field from outside, but in magnetism the magnetic phenomena or magnetic behavior arises from within the material, okay. Because magnetism basically a result of some current flow, electrical current flow, or in the form of a solenoid and so on. So, whenever there is a electric current flow or movement of charge in a continuous manner, we will have some magnetic field generated, and that is the reason in any material you have magnetic field within the system itself, primarily because there is charged species like electrons which are moving and which is going in a circular path around the nucleus, and that is equivalent to a flow of current. So, there is major difference there so far as the dielectric phenomena and magnetic phenomena is concerned. Dielectric phenomena only when there is external field applied to it and the charged particles or the charged species respond to the external applied field in a particular manner, and that gives rise to dielectric phenomena or dielectric constant, dielectric permittivity and so on, or dielectric polarization. Similar thing happens here when we apply external magnetic field in a magnetic material, but in addition, or any material in fact, but in addition all materials because they have some electrons within them, and the electrons, the flow of electrons are basically equivalent to a flow of current. So, there is some magnetism or there is a magnetic field generated within, and that is what we would like to understand in addition to external magnetic field. So, they respond to the external magnetic field, and but they have some origin of magnetism from the inside. So, in a magnetic phenomena what happens, you have a current flowing because these are the flow of current, electrons are flowing, and therefore, you generate a magnetic field, magnetic lines of force, and this is a continuous magnetic lines of force. Okay. The current is flowing in this horizontal path, okay. The electron is moving in this path, and so there is a magnetic field perpendicular to that, and the magnetic lines of force are depending on the intensity and the surroundings, either they will be circular or it may pass through the center of the coil. So, the flow of electrons or the circular orbit actually acts like a current flowing through an wire, conducting wire. Okay. So, you have a magnetic dipole generated even in the absence of an electric field from outside, a magnetic field from outside. So, you have a macroscopic view, magnetic dipoles are already there in the material. Of course, we will find out some of them are effective and all of them are not really effective in that sense. This is a macroscopic scale, but in a microscopic scale you have some magnetic lines of force already all the time present. Whereas, in this case only some dipoles are dipoles are generated only when there is an applied electric field, except in some material where there is spontaneous polarization, but spontaneous polarization here, spontaneous magnetization is always present in a magnetic field, in a magnetic material or almost all the material. Okay. So, that is the origin of the magnetism from the material itself. The relationship here, magnetic dipole moment, is mu m equal to I, current flowing through that, and A is the area of the circular path. Okay. And magnetic polarization J equal to N into mu m is the magnetic dipole moment multiplied by the number of dipoles present. The same thing here also, you have dipole moment, this is q multiplied by d, that means q is the charge and the distance of separation is d, and the dipole polarization is P, capital P equal to small n into mu p is the dipole moment multiplied by the number of dipoles present per unit volume. So, these are some kind of a correlation or some kind of a analogy between magnetic phenomena and dielectric phenomena. As I have mentioned that since current is flowing in around the nucleus in a circular path or the electrons are moving in a circular path. So, it is equivalent to a flow of current. So, if you have a orbit, so that gives rise to some magnetic field or magnetic dipole moment. Magnetic this is, if this is the current flowing in this direction, this will be the perpendicular to that will be the magnetic lines of force. And orbital dipole moment, orbital magnetic moment arises from the orbiting of the electrons around the nucleus. So, this is one kind of motion of the electrons which gives rise to the magnetic dipole moment, and that can be expressed as L, the orbital angular momentum, equal to L, the angular momentum quantum number L multiplied by h bar, h is the Planck's constant, or in other words mu L, the dipole moment, is equivalent to I into A. I is the current flowing and A is the area, that also has been mentioned. So, mu L is the orbital dipole magnetic dipole moment, magnetic moment. I is the atomic circular current which is flowing because of the flow of the movement of the electrons, and A is the area of the orbit. So, this is one kind of origin of the magnetic moment in any material. In fact, wherever the nucleus electron is moving surrounding the nucleus, you have a current flowing equivalent, which is equivalent to a current, and that gives rise to a dipole moment or magnetic moment. So, this is one kind of origin of magnetism in any material. This can be further calculated or expressed in different quantities in terms of other quantities. So, the orbital angular momentum is equal to L h bar, which has been mentioned earlier, which is again equivalent to m e omega r square. Omega is the velocity, angular velocity with which the electron is moving. Okay. So, omega is the angular velocity with which the electron is moving, and that is the origin of the orbital angular momentum. Magnetic moment. So, m e is the mass of the electron, r is the radius of the circle in which the electron is moving. From this one can also write omega equal to L h bar m e r square, and I is the current, atomic circular current within an atom, and q is the charge, t is the time. We have a velocity here, angular velocity. So, E multiplied by V and then 2 pi r, okay, that is the circular path. So, E omega 2 pi, E is the electronic charge, okay, E is the electronic charge. So, magnetic moment mu L, which we have defined earlier, mu L, that is the magnetic moment for one particular electron which is moving, orbiting around the nucleus. Then E omega 2 pi into pi r square, that is the area, that is pi r square is the area. So, L E h prime to m e is the mass of the electron, and that term comes up in the magnetic calculation, magnetic moment calculation or magnetic property calculation most of the times, and that particular term E h bar to m e is known as the Bohr magneton, that is an unit of magnetic moment. So, is called mu b equal to Bohr magneton. So, the orbital magnetic moment ultimately comes to L multiplied by mu b, the Bohr magneton. So, depending on the angular quantum number, magnetic quantum number L, you have the total magnetic moment multiplied by that number, and mu b is this parameter which is fixed, which is constant. So, one can see the orbital angular momentum is actually some integer multiple of mu b, this particular term. So, depending on the number of depending on the value of L, the total orbital angular momentum will vary. To continue further, this we have seen, this is the expression of mu b, and that is, as I mentioned, is a constant number, and that value of that number is 9.274 in 10 to the minus 24 ampere meter square. So, that is a constant which will come across most of the time when you are trying to calculate or understand the magnetic behavior of different materials. Mu b is the elementary quantity of magnetic moments. Orbital magnetic moment arises in multiples of mu b that I have just mentioned. More accurate expression of orbital magnetic moment is, however, it is just not L, actually it is more precisely, without going to the details of that, more precisely one can write orbital magnetic moment is actually mu b root over L into L plus 1. So, it is just not L into mu b, but it is actually a root over L into L plus 1. That is the accurate, more accurate expression of the magnetic moment, orbital magnetic moment. But mu b is certainly an important parameter whenever you are trying to calculate any magnetic moment of any origin. There is one more origin of magnetic moment inside an electron, inside an atom. So, atoms have two different origins of magnetic moment from within. One is we have discussed already, the orbital magnetic moment, the other one is the spin magnetic moment. So, the spin magnetic moment S equal to, in fact, S equal to plus half and minus half, that is the spin of any electron. So, in addition to the orbital motion, it has a spin motion on its own axis, and as it is known that it has two possible spin quantum numbers, one is plus half and another is minus half, and that also, that spinning on its own axis also gives rise to a magnetic moment, and that is called the spin magnetic moment. Mu s, once again just mu orbital, mu s, mu orbital or mu L, which you have used earlier. Mu s is the spin magnetic moment, and which is again the magnetic moment of the electronic spin, that is arising from the spin of the electron, and that can be expressed as mu s equal to 2 into mu b. Once again the same number is coming up, some unit is coming up of mu b, Bohr magneton, and multiplied by s. Okay, s is the spin, and then s is plus half or minus half. So, it gives rise to the spin magnetic moment is equal to mu b plus minus mu b. So, it is either mu b plus mu b or minus mu b. So, the multiplier is only 1. Okay. So, for each electron or electronic spin you have one Bohr magneton equivalent to one Bohr magneton of magnetic moment, and either 1 or plus minus, or plus 1 or minus 1. Once again, just like the mu orbital or mu L we have used earlier, it is not exactly the integer or just multiplied by L, it is L root over L into L plus 1, that is the multiplying integer, a multiplying number. Here also in case of spin magnetic moment, it is just not S into 2 mu B, but instead of it is the more accurate expression is root over S into S plus 1. So, these are the two expressions of the two types of magnetism which originates from the movement of the electrons within an atom. So, all atoms have this kind of a magnetic moment present in them, but depending on the type of the atom and their combination, their crystal structure, they actually come up from the outside. In a macroscopic scale, the magnetic moments will be quite different, and that we will like to see next. The total magnetic moment of a polyelectronic atom, which we have discussed so far in terms of the orbital magnetic moment or the spin magnetic moment, it basically we talked about only one electron. Okay. However, if obviously the atoms have more number of electrons, and they will combine each other and they will interact, and the overall magnetic moment of the atom from the electron we are upgrading it to atom, integrating it to the atom. So, this is an expression for the total ion, okay, total ion having one electron, and mu s, mu of orbital equal to G multiplied by E by 2 m e. E is the electronic charge again, m e 2 m e, or m e is the mass, and G is known as the Landau splitting factor, once again a constant. However, it is an integer, it is a value varying between 1 and 2 depending on the relative contributions of the spin. I am sorry, there are mistake over there. Right. There are contributions of spin and the orbital magnetic moments. That means, in each electron, each atom, we have two different contributions. One is the orbital contribution and the spin contribution. So, the overall contribution is some kind of an additive term, and that additive term is not a simple addition, but it is a little complex, and this is how it is added up. Okay. So, there is a G factor, Landau splitting factor, and this pi total. This is pi total is the total angular momentum. It is called total angular momentum. Okay. So, somehow this is the kind of an expression of the two terms, the orbital magnetic moment and the spin magnetic moment. Now, particularly we will see later on one of our major interest is in the particular group of elements, that is 3D elements, the transition metal elements, and these 3D elements with unfilled 3D cell, the orbital contribution is fully quenched, which means when we are talking about this group of ions or atoms with unfilled 3D cell, then the orbital magnetic moment is almost negligible, and we need not consider compared to the spin magnetic moment, that is negligible, and that is what we call the orbital contribution is fully quenched, and therefore, the ions contribution or the atoms contribution is 2b s root over 2b, that means one of the terms is dominating. We have seen it earlier, this one, this is the spin magnetic moment contribution and this is the orbital magnetic moment contribution. This is almost negligible compared to that. So, we have the magnetic moment, the overall magnetic moment of the ion consisting of several electrons is 2b, what is the spin quantum number, and that is root over of s into s plus 1, where s is the summation of all the electrons. Okay. So, s summation of the spin moment of all the electrons available. So, that gives you the total spin quantum number, a spin magnetic moment, and that is the predominating term. The orbital magnetic moment is negligible in group of these group of materials. With this little background there, so we have learned there is in any atom there is a origin of magnetism or magnetic moment. There are two types of two different origins. One is from the movement of the electrons, the orbital movement of the electrons around the nucleus, and other is the movement of the electrons around its own axis. So, one is called the orbital magnetic moment, the other is called the spin magnetic moment. Well, with this background, let us keep that aside and let us go to the phenomenological description of different kind of materials based on what we discussed initially, that is the permeability and the susceptibility terms, two different terms, and that is the kind of response of the different materials or the atoms or the structure crystals to the external magnetic field. So, both mu r and chi m, mu r is the permeability and the chi m is the susceptibility. These two are the phenomenological description or phenomenological parameter of the materials response to the external magnetic field, and these based on that how they respond to the external magnetic field, based on that there are different kinds of material, there are different types or classified materials can be classified under different groups. These are the 4 or 3 in fact 3 different groups, but they have subgroups. We will find them, we will discuss them in details. So, that the first group is diamagnetic material. So, weak effect, that means their effect to the external magnetic field is fairly low, they do not respond too strongly, and the mathematically one can say that the mu r, the relative permeability is less than 1, is negative, less than 1, and this is negative. Okay. Chi m is negative and this is less than 1. If this group of material is called diamagnetic material and they have a weak effect, they do not respond to the external magnetic field so strongly. The second group is called the paramagnetic and antiferromagnetic materials. Okay. Paramagnetic as well as antiferromagnetic, they respond more or less in similar manner, and once again it is a weak effect, and here mu r is no longer negative, not less than 1, but is positive, is more than 1. So, mu r is more than 1, that means mu r is basically mu by mu 0. So, it is more than 1 and chi m is greater than 0, that is positive. Here it is negative, this is positive, and this is less than 1, this is more than 1. There is third group, ferro and ferrimagnetism, and here it is very strong effect, that means it strongly affects strongly responds to the external magnetic field, and that is because it is relative permeability is much greater than 1 and chi m is also greater than 0, much greater than 0. So, by that they are characterized. So, this group of magnetic materials are of tremendous importance from the application point of view. We will look into that later. Now, ideally there may be one group, because here we have see it is less than 1, less than 0, these are all more than 1, more than 0, and this is much more than this value. So, ideally there should be a situation where it is somewhere in between, that means mu r is exactly 1 and chi m is exactly 0. Ideally that should be there, but in reality it really does not exist, either it is slightly below or slightly above the 0 value, 1 and 0 values. So, ideally it can have, but really in reality does not exist. So, this is not a group of materials of our interest obviously, because such materials do not exist. We have only these 3 groups, and these, I am sorry, once again there is more, sorry, I should correct that. There is 2 problem of serial numbers. And then this should be 4. Right. Sorry, there are some problem of serial numbers. So, we have 4 groups actually. 4th does not exist, other 3 really exist, and out of these 3 groups, 2 of them have 2 subgroups, as it is mentioned here, paramagnetic and antiparamagnetic. They are so far as these parameters are concerned is same, but their behaviors are different, their many of the other properties are quite different. We will look into that later. Similarly, you have 2 groups here, so far as these properties are concerned, they are identical, but they again have different other properties. We will look into that later. I have to correct it once more. Right. Okay. Now, we look at some of the other aspects of these groups. First of all, the diamagnetic or diamagnetism. The basic requirement, atoms with completely filled orbitals. Okay. So, one of the requirement, the elements which have completely filled orbitals like inert gases, they do have this kind of behavior, diamagnetic behavior. That means their mu r is less and chi m is also less than, sorry, mu r is less than 1 and chi m is less than 0. No magnetic moment without applied electric field. Just because they have a filled cells, in principle they should have a magnetic moment, but they do not generate any magnetic moment. So, the compensation of spin moments. So, each one of them has a negative and positive component. obviously they cancel each other. The orientation magnetic dipole, the orientation, this is the kind of orientation in the absence of a magnetic external magnetic field. So, since they are all field cells, there is no unfilled cells. So, there is no internal magnetization or magnetic moment, and in absence whatever small magnetic moment are there from the dipolar magnets, they are aligned antiparallelly aligned with each other. However, when you apply magnetic field, if there is a magnetic field, this is your material, you have magnetic lines of force, because of this value and because this chi m is negative. So, the magnetic lines of force are repelled by the diamagnetic material. So, diamagnetic material really do not like the magnetic lines of force, they on the other hand repel them. And the inert gases, ionic crystals, semiconductors, metals like this, which is mostly the field orbitals, will have this kind of a property. Okay. So, this most important thing is the rarefaction of the magnetic lines of force through the diamagnetic material. Comparing to that, paramagnetism is like this, and this is the kind of orientation of the dipoles, or the in absence of the external magnetic field, this is the dipole moments, whatever is there, they are kind of random orientation. The atoms with partially filled orbitals, okay. Here it is atoms with partially filled, earlier it was completely filled, here it is partially filled, feeble magnetic moment in absence of applied field. So, even in the absence of the magnetic field, they have a very feeble magnetic moment, and the disordered arrangement of the magnetic dipoles. So, mostly the magnetic dipoles which are there upon each atoms, they are in the disordered form, and in absence, in the presence of a magnetic field, when we apply a magnetic field, they like to get concentrated around within the material. So, compared to the diamagnetic material, where it was repelling, the magnetic lines of force were repelled, here it is attracted. So, there is a little bit of concentration around or within the magnetic paramagnetic material. The examples of such materials is alkaline earth metals, oxygen, aluminum, tin and platinum, etc. Okay. So, these are some of the materials which are as a paramagnetic, they are very weak magnetic materials. Next is ferromagnetic material. Here of course, there is strong magnetic effect, atoms with partially filled orbitals, primarily the d cell orbital, and then large magnetic moment, spontaneous magnetization, presence of magnetic domains. Okay. It is identical or analogous to ferroelectric material in presence of the electric field. So, they have a large magnetic moment, spontaneous magnetization. So, even in the absence of a magnetic field, they are magnetized, and the presence of magnetic domains, that also give rise to magnetic domains, just like ferroelectric domains we have seen earlier. So, within this domain, the magnetic moments are aligned in a particular direction. However, the neighboring domains may have a different orientation. Most important thing, in the presence of a magnetic field, they get strongly coupled with the ferromagnetic material. So, the lines of force gets concentrated and passes through the magnetic material. So, their coupling is quite strong. In other cases, the coupling is quite weak. The materials like iron, cobalt, nickel, these are 3 transition metal elements have a strong ferroelectric effect, ferroelectric property, and of course, their alloys also. Okay. So, these are ferromagnetic materials, and iron is one of the major or the most important element or member of this group, and in addition to cobalt and nickel also have the same similar properties. So, this is where the strong magnetic coupling takes place with the external magnetic field, and that is why mu r is much greater than 1 and chi m is also more than 0. It is actually positive. This is antiferromagnetism. In fact, earlier we had 3 groups, now we have 5 groups including the 2 subgroups. So, antiferromagnetism was coupled with or combined with paramagnetism, which is very similar behavior so far as the external magnetic field is concerned. However, their origins are little different. Here once again atoms with partially filled orbitals, the magnetic moment, full compensation of the magnetization by antiparallel alignment. Okay. We will look into this what exactly it means, but basically it is given here to some extent that each magnetic moment has an antiparallel pair. Okay. So, each of them are cancelling each other. So, exactly the same magnet quantitative value, and but the direction is different, direction is just antiparallel. So, there are pairs of magnetic moments having the exact same value, but in opposite direction. So, individually they have magnetic moments, but for some reason or other they have an antiparallel ordering, and because of the antiparallel ordering the overall magnetic moment is 0, almost very close to 0, and that is why chi m is very close to 0. So, it is a weak magnetization very similar to paramagnetic materials. So, that is the reason they were combined together. Okay. But individually each atom has a strong magnetic moment, resultant magnetic moment, but when it is combined in the crystal structure in a particular structure they get them aligned in opposite directions. So, the examples are basically not metals or elements, in this case primarily is the oxides like MO kind of oxides, MNO, FeO, NiO, CO, all of them you will find, you will remember all of them have a rock salt structure, sodium chloride structure. So, they have identical structures, and because of their interaction between them, the magnetic moments are aligned in an antiparallel manner, and that is the reason this group of materials is called anti-ferromagnetism. So, compared to ferromagnetism where there is a parallel alignment, here is an anti-parallel alignment, and therefore, its name is given as anti-parallel anti-ferromagnetism. The last group in this series is actually called ferrimagnetism. This is very close to ferromagnetism, but the relation or the origin of this magnetic behavior is slightly different, and that is why although they are strong magnetic material like ferromagnetic material, strong magnetization, mu r is much greater than 1 and chi m is also more than 0. So, very similar to that of ferromagnetic material, but they are not called ferromagnetic material, they is called ferrimagnetic material. So, this distinction must be remember that although their behavior is more or less same in many ways, but the origin of the magnetism or the response to the external magnetic field is slightly different. Sorry, response to the magnetic field is different, but the origin response to the magnetic field is same, but the origins are different, and that is why they have not been termed in with the same name, there one is ferromagnetism, another is ferrimagnetism. You will see one thing here, you can see the coupling with the external magnetic field with ferromagnetism, and ferrimagnetism is almost identical. Okay. So, they can be used more or less in the same purpose, because they have the same kind of properties. Okay. Now, coming back to the paramagnetism and diamagnetism, which are weak magnetic materials, and therefore, they have some kind of linear magnetism or linear, just like linear dielectrics. Here also one can say linear magnetic materials, because the polarization versus the external magnetic field H, J versus H carb is linear. However, there is one difference between the two magnetic materials. One, the red one is the paramagnetic material, it has a positive slope, and the black one is diamagnetic, it is a negative slope. Okay. So, that is one of the major distinctions in addition to what we have discussed earlier. So, this is one way to distinguish between paramagnetic material and diamagnetic material. Both of them are weak magnetic materials, their response to the external magnetic field is fairly weak. However, one responds completely differently than the other. Paramagnetic material has a positive slope, so far as the polarization is concerned, magnetic polarization is concerned, whether on the other hand diamagnetic has a negative slope, but both of them have a linear slope. These are some of the examples and specific values of susceptibility for a group of diamagnetic as well as paramagnetic materials. This is, you can see here, most of them values are in the range of 10 to the power minus 5, but all are negative, and there are slight variations, but more or less in the same range. Aluminum oxide, copper, gold, silver, silicon, zinc, metallic zinc, sodium chloride. Sodium chloride and aluminum oxide are two compounds, they have also the similar range of susceptibilities, and they are diamagnetic materials. Okay. Here on the other side, aluminum the paramagnetic materials are aluminum, another set of elements, and also some compounds like aluminum, chromium, molybdenum, sodium, titanium, zirconium. And as you can see, one thing is, you can see the susceptibility in both the cases in the order of 10 to the minus 5, whereas one is positive and there is just negative, otherwise they have certain amount of similarity. And even manganese sulphide has 3.7 in 10 to the minus 5. So, this is just to give you an idea what is the range of susceptibility of different groups of materials, like but particularly the weak magnetic materials like diamagnetic and paramagnetic materials. Temperature dependence of particularly the paramagnetic materials, paramagnetic susceptibility, it is a as temperature increases, the chi m or the susceptibility decreases, which is quite understandable, because basically in a crystal or in a solid there are atoms, and each atom has some magnetic moments aligned in a particular direction, and these atoms, because of the temperature rise, there is a more of randomness because of the thermal vibration, and that decreases the susceptibility. So, whatever small susceptibility it has, still it further decreases, and it is a kind of parabolic relationship. or inverse relationships, not parabolic, inverse relationship. So, one can plot and express this chi m as a constant, C is a constant and T is the temperature in Kelvin. Compared to that, whatever we have seen earlier in a table, the susceptibilities of the order of 10 to the minus 5, either positive or negative. Compared to that, if we go to some of the strong magnetic materials like ferromagnetic materials, the strong magnetic materials are also there like ferrimagnetic, we will look into that later. Ferromagnetic materials, the susceptibilities, or these are not susceptibilities, I am sorry, this is permeability, mu is as it is mentioned, is much greater than 1, and these are of this order. Magnetic iron is 200, nickel is 100, permalloy, which is a permanent magnet, an alloy of nickel and iron, about 8000, and another alloy, again a permanent magnet, 75 is to 75 nickel and 18% iron, and in addition to about chromium and copper, some amount of. Now, these are different phases, these are not pure elements, and different crystallographic phases will have a different property, and one can, by that process one can increase the magnetic permeability to the order of about 20,000. So, that is very important. So, they can respond to the external magnetic field very strongly, and they can be they are basically ferromagnetic materials, and they can be converted into a permanent magnet. Okay. So, where the magnetic lines of force will remain there and it will not destroy. So, in other cases, because of the weak magnetic response, only when the magnetic field is applied you get a induction or polarization, whereas here the polarization will be permanent and one can get a magnetic field generated out of it. So, the time is almost up. So, we will discuss this further in the next lecture. Thank you for your attention.